leader for materials and molecular science theme at SCD. You cannot hear me. I need to speak louder. Like this is better? Okay, good. They want to shout. And so I'm the lucky one who is going to give this talk on behalf of roughly 42 people. So besides the audience in front, I also have the audience on the back, carefully watching and writing down anything I say. So as Paul said, this is about showcasing at a very high level the capability we have in modeling and simulation. I'm not going to talk about the science or the research we have been doing, so you're not going to see fancy scientific application. I'm just going to present you the software and the software capabilities. So before going to the terabytes, so there is something that with Paul we thought would be good to touch explicitly. So typically, if we have a technological application, behind there is a material or a set of materials that need to be integrated in a device. And as far as STFC is concerned, we have the large-scale facilities that work a great deal in characterizing the chemical composition, the electronic and atomic structure, but also the electronic and atomic dynamics. And then these together generate a macroscopic properties that needs to be integrated in a device. So for most of the facilities, the work is at the level of this characterization and then touching on the properties. However, there are also some facilities for which the device integration and the engineering is relevant. And this also requires some computational material science. So here, for instance, if you think of laser targets or material for detector and scintillator, some of your users might be interested in this technological application. So this, in principle, I'm told, might be in scope if there is an interest in going in that direction. Right. Now, at SCD for the last year, we have been trying to come with the perfect workflows encompassing all the work at all the STFC facilities, and must admit we have failed blatantly. We have different versions. One is even 2A3 form that has each and every beamline we are aware of between ISIS and Diamond and CLF, but that is very complicated. So for the purpose of this presentation, that is basically to showcase the capabilities, then the slides have been shared and there is hyperlink. So if you want to do some homework to get into the details, you can have it, because in 45, 50 minutes, I'm not going to cover it all. And each and every slide I'm going to present would entail a full seminar to be very clearly explained. Okay, so I'm going to stay very high level. So this is the version we think makes things more accessible. By the way, I repeat myself, I don't think in any way that this is the perfect version. So we typically start from a measurement of the facilities, and the measurement is enabled through software. So you have software for control, the software generating the beamline. So this is also software enabled. Then the measurement needs to be typically analyzed, and this includes post-processing. And this is the software for post-processing the experiment. And all the facilities have their own teams working on this, because no software for analyzing the experimental data, no science. It's like a little bit like Martin. Then if we want to interpret, in an ideal world, you would have a magic modeling and simulation or theoretical approach that can be directly mapped into the analyzed experimental data, okay? And you would have a comparison between experiment and simulation. Now, since experimentally you cannot measure the potential energy surface of the electron ion interacting, in practice, there is always a step where we need to somehow post-process the output of the modeling and simulation and make a contact with the interpreted experimental data. And from there, we can generate new science and new knowledge. So for instance, when we start post-processing, we can try to extract an observable feature which might not be directly measurable. But we can also try to bridge through simulation between different measurements, especially when you have structure and property. Okay? And here you have little numbers on a black background, which are the software classes we think constitute this ecosystem of software infrastructure. So in a sense, they are all important if you want to bridge between the experiment and the theory of yourself. As the color gradation gradient in this arrow means, this is an extremely wide workflow, and you need people with different expertise. So these people need to be able to talk to each other and also understand. And this is where sometimes things get lost in translation. Okay, so this is not a job for one person. This is a job for 50 people, because you really have different language. I don't have a clue about synchrotron control requirements. I've been working on first principle simulation. I know a little bit of my field, but I really cannot go to the facility and say, now you need to use this detector. And the opposite argument might be valid here. So if we manage to talk effectively, we really can create added value. Who does theory and simulation at STFC? Well, at the moment, we basically have a very complex ecosystem where we have facility-funded projects, we have users and collaborators with the beamline, and then we also have a set of different community tools which might or might not be used. So one of the aims or ambitions of the LC is to try also to coordinate not only this workflow, but also the interaction from the outside, because we cannot be a black box. We need to find a way of integrating different sources of theory and modeling and also software. Okay? To try to facilitate the work of the facility in requesting the stuff from the ALC, we have tried to minimally expand here the modeling and simulation workflows. So basically, again, this is one size fits all, is difficult, but we have tried to abstract. So you might be, or you might not be certain of the stoichiometry of your sample, especially locally and in time. So if you do operando spectroscopy on battery or electrochemical system, locally your stoichiometry is going to change. So you might start asking questions like, do I know the stoichiometry of the sample I'm measuring or not? And either ways, you can start using theory and simulation methods to try to answer this question that you cannot reply experimentally only. Now, assuming stoichiometry is not a problem because you're using on a single crystal and you exactly know what is there, then there is the question, do I know the structure, static or dynamic? And again, if that has been previously measured, the answer is yes. If not, you can benefit from using theory and simulation, which boils down to be able to compute an energy for your system, the forces, and then propagate dynamics on a potential energy surface that depend on the energy you can compute. Okay? If you're so lucky that you know the stoichiometry of your sample and you know also the structure of your sample, then you can start asking questions like, is there any property of this system that I would like to know and understand? Maybe my users. No, I'm going to give an example. We specialize in structural solution for dissolving materials, and my pesky users now wants to talk about chemical reactivity. So my facility can measure a sample average structure, but the chemistry happens out of equilibrium through a fluctuation. How do I go about that? So some of these pesky questions are coming or might be starting to come from your users because they always want more complex, more beam time, more unlikely experiments, operandi. Okay? So, and also here when it comes to properties or response function, theory can play a role because it can try to chase what you measure, but it can also try to look at aspects that you cannot directly access in the experiment. And by interplay of these two strands of work, there may be some new useful idea which can contribute to the user's experience. Now, for you or for the experimental facilities, you have the experiment and the interpretation. For us, since we also specialize in theory, we are a little bit more abstract and something where we see a great deal of opportunity of doing some collaborative work and also trying to move the dial, also in collaboration with the communities we routinely collaborate with, is about these pushing the reach of the methods we have to try to answer these kind of very fundamental questions that might appear detached from the experiment, but they actually are not. So like, for instance, how do we correctly describe the motion of the atoms? How the electrons can get redistributed, for instance, following an excitation of the electron degrees of freedom or also the spin electron of freedom. How the electrons get redistributed if the atoms start moving. So the spectroscopy of dynamical objects. Is the atom dynamics classical or quantum? Are the electrons hot or very hot? So these are questions that, if followed, each of them goes through very deep rabbit holes, and it's not one project that can answer this. So it's really our major let's say, challenges for current landscape in theorem simulation. And as I see, we might be able to contribute also in terms of software infrastructure and workflows. Okay? So don't be shy to ask a very ambitious question in your request. To simplify, try to further help you asking us question, regardless of whether you believe that this workflow is representative or not of your beamline, your users and your beam scientists are gonna bang their head against questions like this. So the first one is, if I want to use simulation, can I set the inputs correctly? If HPC is needed, can I use it properly? Can I have access to it? Can I understand what the simulation program prints out? Can I link it to the experiment? Then am I capable of navigating the accuracy viability trade-offs that any simulation method entail? Because the Schrodinger equation has been out there for a while, but if there are more than 3 interacting bodies, we cannot solve it analytically. So we go numerical, which means we need to cut the simulation. How do we cut it? What do we cut it? This is the fish market where everybody has a strong opinion, knows best than the others. But as we could try to coordinate these kind of answers. Of course, in trying to answer this pesky question, there is a great potential for machine learning and artificial intelligence that are not put here. So typically, if somebody is an expert in a method, and this applies also to the beam scientist, you get to answer the same question 25 times per month, because each and every user who does not expert asks you the same. And perhaps there is also some scope of trying to play a little bit with artificial intelligence and trying to see if we can automatize the answering of the simplest question. Besides, of course, documentation writing, that is also something that takes a lot of time. It's not so glamorous, but is very. Then, last but not least, can we easily visualize and compare experimental and modeling simulation output? Because if there are many simulation codes, in terms of visualization, there is also an abundant offer. They usually are developed with one specific community or set of observable in mind. But at the moment, at least in SCD, we do not have a kind of general purpose platform that can be used interchangeably by different communities. This is something that might be of interest to some facilities. Right. So here, before I had used boxes for the software for 1 to 4, and I've expanded these software classes from 4.1 to 4.6. So when you start to formulate your priorities, it would help us a lot, but a lot, if you already internally would start thinking, am I asking a 4.0 or am I asking a 2? So we are going to try to be able to discuss at the next workshop how also to balance what you need. Because we just don't need beamline specific. We might not be needing only beamline specific software. If you want to improve the link with theory, you might also need to have some work on the other side of the bridge. Right, okay. So let's try to show you something for you to see what we have been doing. In our team, we basically have 40 people, and we specialize in different software and methods that offer a multi-scale modeling and simulation platform. So typically, if we have different modeling possibilities in terms of level of theory and also level of choice of code, the bigger the system your modeling gets, the worse the accuracy becomes. Okay, so if you are dealing with I don't know, a few atoms, and you're interested in basically no time dimension, you can go very accurate. But as the size of the system increases, also the time scale of the phenomena you want to follow increase, you need to start making the description of the matter a little bit coarser. And there is a big divide that here is arbitrarily put around 1,001 million atoms, whereby we need to get rid of the electron degrees of freedom and start to treat them implicitly. We also have in the theme capability of bridging these two worlds with and without the electrons, and I'm going to give you a few examples and how that could be used for a STFC facility. In the last 4 to 6 years, there has also been a revolution ongoing, because with the development of machine learning techniques, we now can have what are called machine learning interatomic potential that basically allows you to cheat. So you can get the accuracy of first principle methods, but you can bring it to a few thousand atoms if you're interested in energies and structures. You're not going to get the electronic structure. But this is something we, as you're going to see, we are already working, and we would be very happy to start expanding the offer. So we have recently restructured, which means that at the moment we are 40 people distributed across 4 groups. It goes from classical materials and molecular modeling to multi-scale material chemistry to data-driven materials and molecular science to theoretical and computational material physics that needs to be split because the moment is 20. And people in this group are basically expertise and track record in developing software across all the classes from 2 to 4. Slides are going to be shared, so there is no need to make pictures. Right. Now, I'm not going to go through that, okay? So the slides are going to be shared, and they're going to be hyperlinks, okay? So if you wanted to get the best, the most out of this presentation, if you can go 5 minutes on your spare time and try to click if there is something that you are interested in, it's going to be more useful than me spending 20 minutes going through each and every piece of software. I'm not going to do it. I'm a nice guy. What I'm going to just say is that in the presentation, you're going to see the software that we are been developing and maintaining organized through the same software categories on the first slides. So you can see here, for instance, we have software 2. We have software. We have been involved in developing software like the LX curve that can be used for direct experimental data post-processing. Okay. Oh, sorry, I need to work out a little bit the angle because I'm getting old. We have the same in terms of experiment post-processing, and this has been developed with the ISIS for elastic neutron scattering, for quasi-elastic neutron scattering, for muon spectroscopy. We also have some software that links to electrochemical quartz crystal microbalance experiments with the aim of then linking to operando core level spectroscopy. Only the first half has been done. We have other software in terms of visualization, in terms of stoichiometry resolution during electrochemical cycling. Then we have a plethora, or we have experience in a plethora of first principle code. So these are the codes that compute you the energy, the forces, and allow you to propagate dynamics for your system, and also response function. And we have co-developed a few of these. Now, first principle, as the clue is in the name, these are first principle methods. So in principle, I'm doing some pun, there is an approximation. So as a result, the input preparation is very easy. The computation is intensive in solving it in using this code, but they are relatively forgiving when it comes to preparing the input. If you are interested in studying phenomena or materials at bigger length or time scales, we need to start taking some approximation in terms of the description of the interaction in the system. And these are the codes like, for instance, here, the poly, that they use a parameterized Hamiltonian. When we move to a parameterized Hamiltonian, the computation is simplified, so they are less expensive computationally. We can tackle bigger and longer system, but the preparation of the input becomes unforgiving. So there needs also to be a software infrastructure that helps the user to not mess up things when setting up the inputs. We can also push things further and reach in the coarse-grained mesoscale regime, and where we start coarse-graining the matter, so we can model even bigger system and for even longer time scales. Clearly, there is not one code for all the experimental STFC. And this is also part of the discussion that needs to be ongoing. Because only by talking and trying to understand what we can use for a specific problem, or maybe what we can combine for a specific problem, we might be able to do something really exciting. And there is a great potential of doing that. We also have substantial experience and track record in the use of multi-scale QMMM chemistry method that try to bridge the scale between first principle methods and methods that are suitable to describe matter at a parameterized Hamiltonian level, where basically the computation is concentrated on the experimentally intensive part of the system. We have also a wide selection of a same level of software infrastructure in terms of machine learning potential. So again, here we can propagate dynamics, optimize structure based on machine learning potential that have been previously learned on DFT result. We have a wide selection of software for input setup and workflow management. And these are for different fields, going from, for instance, coordination of complex workflows to calculate inelastic and elastic scattering channels for electron imaging damage, at the level of setting up the simulation of a macromolecular system for soft matter. So there is really a lot. And going through it is very difficult because each and every of these codes would require a presentation by itself. So the aim of this presentation is you get the slides, you have the links, you might be seeing where you work. So for example, if you work in core level spectroscopy, you might not be interested in, I don't know, resolution of the structure of lipidic bilayers. And then we are very open to keep the conversation going. Okay? So we do not think in any way that this is going to be exhaustive. So this is just to maybe steer the questions, not to answer them, because it's impossible. There is just too much stuff. Very quick postscriptum. So the list of software is the software we develop and maintain. We also know how to use other software. So if you want to use other set of codes, or you want these other codes very popular among your users to be included in the software infrastructure, we can do it. And most likely we have also been using them for validation purposes. I'm not going to go through this wall of text slide, but this again is for some food for thought in case you come back to these slides in your own time. Because if you want to develop the modeling and simulation offer within the ASC that tries to meet the needs of your users have different needs. So there's not going to be one size fits all. And this slide basically tries to invite a reflection on this. So first, that if the software, once it's developed, for it to be uptake, there is also additional work to be done. So it's not that just developing the software and releasing it guarantees a massive uptake. So we're going to have to work together if you want these new solutions that are reaching your users. Then, simulation and modeling costs core hours. So depending on the accuracy you want and your users need, there's going to be the question, can we actually run this on SCAF or not? Or if not, then we need Archer or other super computational platforms. How we're going to make sure that the users can access it? And just raising questions, I'm not offering answers, I know. Then this might be controversial. So if you wanted to embrace for a second the software classification on slide 3, where we go from the experiment to the theory development, software closer to the beamlines tend to show value at the beamline faster than software far from the beamline. So if you want a beamline specific software front-end solution, that can be done, and it's certainly within the ASC scope. But if you want to balance, there's going to be some discussion that we want to have, like, where do we want to invest? Okay. Then, if we go theory and we expand the modeling and simulation, these are also useful to make contact with non-STFC experiments. So typically lab scale experiments or EPSRC facility experiments, because STFC doesn't measure it all. Measure a lot, but there are also other facilities. And here you know better than me what is the complementarity of your STFC beamline with other EPSRC initiatives in the field. In this presentation, we have not touched a lot on ASC data and machine learning theme, and this has been done on purpose because that again is something that is best done collaboratively, and we don't know yet the request. At least so we can discuss once we know the request how we better match everything. Then, on record that we are super flexible in terms of answering and trying to adapt to your requests, and we are fully aware that depending on your needs, in some cases you might want just software provision, because we have quite some expertise in software engineering and distributed parallelism, and more recently GPU porting. In other cases, you're going to want in silico added insights, And in others, you might want a true scientific collaboration or partnership. So we're not going to force anything. And we are fully aware that your needs are going to be different. So, and Paul can act as focal point of this, washing my hands, this request, okay? So if you want just software provision, that is fine, don't feel bad, it's fine. If you feel the software provision combined with some in silico, some further insight from simulation is better for you and the user, that is also fine. You want to submit extra grants follow-up activities, that is also fine. You're super flexible. But truly. Okay, now in the next 20 minutes or so, I'm gonna brush making 40 people resentful towards me about some of the software we have been developing. I repeat myself, each and every of these slides would require a dedicated seminar, okay? So I'm not aiming to explain it in the best possible way. I'm just, I can say, showing, highlighting them in case that you may want to follow them, because we believe these are relevant for the activities across ISIS, Diamond, and Sierra. Okay. And in doing so, we're going to follow in the software labeling that I've introduced on slide 3. Okay, so you're going to see 2, 3, 4.6. What is that? Is on slide 3. If you get back to slide 3, you're going to see it. We're going to start close to the beamline. So, for instance, we have been developing in very close collaboration with ISIS, actually, and the mounted team, in what is called ABINS, which stands for Ab Initio Elastic Neutron Scattering. So, this basically is software that enables you to directly compare, taking into account of beamline specific elements, such as, for instance, the convolution resolution, experimental and calculated inelastic neutron scattering data. It comes with a very nice graphical interface that allows you to compare experiment and simulations. And now this started specifically for one beamline, but then since it has been so useful, it has started to be used also on other beamlines. And perhaps more importantly for the ASC, since you can simulate the experimental and calculated spectrum even before making the experiment, you can also, and these experiments depend on the detector, which might, and on the beamline, which might be different between different neutron facilities. You also start comparing what you would get on different beamlines at different facilities, which might be good for the user planning and experiment. Okay, this is software enabled. And here you can see some other capabilities of zooming in at the level. You have 25 million different options. I'm not even going to go through. You have a link and you can look at that if you want to see the level of details and also the utility of this graphical interface. We have also been involved in something that is really back-end facility software, which is basically this euphonic project, again, inside the base ISIS project, which stands for Proper Analysis of Coherent Excitation, where we basically have developed an external Python and C package that can integrate can do Q-point sampling to decide or to help the user decide where to focus the attention in the experimental data that is massive, and these are for these lots. It has also been parallelized, so what used to take overnight now can be done in 1 hour. And so this is another example of an impact for the users, because they have 3 days beam time access, they get a deluge of data, they need to decide where to look in the data that they're measuring, and in 1 hour instead of overnight, they can get some indication of where the fingerprint is or what they're measuring. Then, again, along the lines of creating a link between post-processed quantities from simulation and post-processed quantities from experiment, we have also the spin excitation version of ABINS, which has been called in tone. This is a kind of preliminary prototyping work, where we basically, the aim is to get first principle responses, so typically magnetic susceptibilities, and then try again to link to the dynamical structure factor that is measured at ISIS, and from there also try to interpret and design experiments. There are also some nitty-gritty about the experiments in aligning the crystals, and these things are being explored in terms of simulation. Staying on the software that helps the interpretation of the experiment, we have also been active in another project in collaboration with ISIS, and this is the MDMC, where basically the idea is to get not only is to obtain parameters from molecular dynamics, which allows you to propagate the dynamics of your system by leveraging on the retrofitting of the structure resolution. So you basically analyze structure and you get information on the parameters that allow you to propagate the system. And at this moment in time, so the idea is from ISIS, because there is a proof of concept in this technical report, and the work has been focusing mostly on restructuring the software and the software base of this idea so that you could use different molecular dynamics engines. So in a sense, a software refactoring. And then, of course, since the ambition, like hope, is never ending for human, now there is also work going on in not only getting the dynamics, but also the diffusion coefficients out of parameters that have been fitted from the structure. This is one case where we work on a specific set of experiments, then we try to bridge to other observables that are measured in other beamlines or facilities. I'm not forcing, I'm just suggesting. Keeping with the catalog, we have also been working in supporting ISIS muospectroscopy endeavor. Now, this has been a project that has been going on for a few years. So it is very mature and has generated output in different direction, because it started from, let's find the muon stopping site using DFT simulation. Then it moved to a software to follow the spin dynamics of a system with a muon implanted. The appetite grew touching on muon quantum effect, because the muon is very small, so it cannot be really classified as classical. And the muon quantum nuclear effects are very important for muon spectroscopy. And more recently, also prompted by the use of negative muons at ISIS, we have also created a atomic Dirac solver to calculate muonic X-rays. Now, this is very sustainable in the way it has been implemented. So you may know that the established atomic solver of Dirac equation are based in Fortran 77. So this has been written in a Python and can be used or interfaced for other applications. For instance, for X-ray cross-section in the 70s, in principle, there could be the possibility of trying to build on this standard of reinventing the wheel. Because, nothing because. I wasn't going to sell it, I said I would not sell anything. Okay, so we also have software that allows interpretation of a electrochemical quartz crystal microbalance experiment. And the reason why we did this was that this technique allows you to quantitatively resolve the stoichiometry during cycling, but if you have more than 2 electroactive species, you end up with a system of an underdetermined system of equation that you cannot solve. So you basically have more variable than equation. And we have coupled, to solve this stalemate, we're basically using a DFT energy screening to try to screen on an energy basis the solutions that are compatible with the experiment. Who cares about this? With the idea of providing a local instantaneous stoichiometry to help the interpretation of operandum measurements for system under electrochemical control. You have the link. The software comes with a proto-artificial intelligence. We don't even call it artificial intelligence. A proto-software layer to steer the preparation of the input. So you don't have a clue how to run the simulation for a magnetic system, and you have some modules to do it for you, and they do it for different, very popular codes, starting from custom. In terms of simulation from first principle, as I said, we have different codes. So here, I'm going to cut it very short, probably because this is the field where I work, so I want to make sure that it remains as unexplained as it can be. So these are different codes that allow different numerical accuracies, and they have different functionality available. They also have different stage of maturity, which means they have different documentation and ease of use. So we're very flexible in terms of DFT. Now, Keith is here, so clearly I put faster first, incidentally. But so if you really want to ask what is the best DFT code, at least please explain or specify the application, because otherwise we are not going to be able to help you very much. We are experienced with a variety of this. And of course, we can also link our strength with other strengths that are available in the campus. So in terms of workflow management, now this is very complicated, so I'm going to keep it very high. So with the ambition or the aim or delusion of trying to help Diamond in navigating the imaging damage compromise, we have also written a Python suite that allows a coordination of different levels of theory and also experimental data to try to work out energy loss channels, but also primary and secondary scattering electron mean path, with the aim of trying to understand the damage in a material. So typically, if a material gets locally excited by a photoirradiation, does this affect the resilience to electron scattering damage? We are writing a paper with the answer. I'm not going to tell you the answer because I said I wouldn't talk about the science. So this is just an example of something that an experimentalist, even a theory-oriented person, would struggle in coordinating, because there are different sources, different codes, different level of theory, combined with experimental data from NIST. But the software can enable it. So this is also something we could do within the SC. We are also interested in excite state properties and specifically aggressive excitation of the materials. And to this end, we have started to implement a specific flavor of theory that is quite convenient to calculate nonlinear optical effects. Again, we're thinking about damage. And so this has been going on and basically has already been committed. And if you actually have some nasty application where local excitation might be important for damage, this is something we would be very happy to explore. Right. So far what you have seen has been all based on the explicit description of the electrons. I'm going to move to the realm where we treat the electrons implicitly. And also here in SCD, we have a battery of very mature software that has been developed over the last 20 years. And this is probably most to be explored from the facilities. So here you can see the slide about the poly. This is a molecular dynamics propagator based on parameterized Hamiltonian. So you simplify somehow, you parameterize the interaction between your atoms, and then you can propagate the dynamics. And it has been used to different systems, going from the bio to the inorganic to also, where is it? Here, the mixed organic, inorganic system. As I said, when you move to parameterized Hamiltonian, the simulation gets cheaper. Getting the input right gets more complicated. And to face this reality of life, the software comes also with complementary software suites that help the user to set up force fields and also to pass from one force field to another. And this is the DL field program. A lot of information. One thing that the DL software offers, and this is not so common between different force field codes, is that this software allows you also to match force field for organic and inorganic stuff. So for those working on a hybrid organic inorganic system, this is something that where we could further develop the infrastructure. And here, for instance, you can have a system, a series of examples that have been treated at the level of DL poly thanks to DL5. So polymers, lipid membranes, molecular cages, biomolecules. Here you have organic absorbate in an inorganic catalyst, very inorganic system, and also more adventurous system like interfaces between a bioinorganic, an organic system like cellulose and graphite. Besides molecular dynamics, we also have software for solving Monte Carlo and or using Monte Carlo capabilities. Okay. Reducing the terabytes in this slide to 1 or 2 sentences. Microdynamics propagates things in real time. which means you have limits about the real time you can follow. There are alternative methods like Monte Carlo that are stochastic, that allows you to overcome this limitation of electrodynamics and are quite useful to obtain thermodynamic properties and phase diagrams. So if you have a phase transition, and again, the accuracy of this method depends on the accuracy of the potentials. So this is something that between the facilities, especially those working in phase change materials, we could try to expand further and make contact there. We also have a variant of kinetic Monte Carlo, which is named kinetic Monte Carlo, specifically adaptive kinetic Monte Carlo. That is another way of going beyond the limitation in time scale of molecular dynamics. So for molecular dynamics, typically you cannot reach beyond the microsecond. With these adaptive kinetic Monte Carlo approaches that do not require a priori any information apart from the interaction between the systems, you can follow dynamics on a second scales. And this could be useful if you're interested in damage, however it is generated. Last but not least, we also have capabilities in terms of mesoscale methods like dissipative particle dynamics or lattice-Boson equation, where we lose not only track of the electrons, but also the individual atoms, and we start describing matter with grains. And this can have application for fluidodynamic or rheologic problems. Whether this is of interest or not, I don't know the facility, but in case, we can discuss this at the workshop. We also have software solution to bridge between these two realms of matter description, which is this multi-scale QMMM, where we basically use the atomistic parameterized Hamiltonian description for the bulk of the system, and we focus the quantum mechanics on the reactive part of the system. And this is basically, although being a well-established methodology, so there was also a Nobel Prize in chemistry awarded for that, is yet to be discovered at STFC. And it has a lot of potential because it allows to increase the accuracy in the QM region, cutting the computational accuracy in the bits in the parts of the system that are not important. And for instance, it has already started to be used in collaboration with Diamond for this serial crystallography experiment, where they basically follow a reaction path by taking X-ray structure resolution of the different intermediates in the reaction. And this can be coupled with this QMMM approach. And as byproduct, besides refining the structure and also keeping track of the hydrogen that by X-ray crystallography are not immediately detectable, one also obtains the potential energy profiles for the reaction, which you cannot measure. The same goes for using the QM description to extract linear and nonlinear vibrational properties. And there is a ARC project proceeding along this line. And this can be a powerful fingerprinting for chemical application because you have vibrational spectroscopy, but you also can get the energy of the intermediates. You could also get correlated spectroscopy if needed, or other vibrational response function. Again, the trick of focusing the computation on the QM active part of the region and reducing the cost of the on the outside of the reactive side can also is very convenient also for excited states with some caveats. This is something that also we could try to explore within the ALC. Same goes for excited state dynamics, either through surface hopping or in ultra-fast real time. So there are possibilities in case, especially for the facilities that are interested in excited state dynamics. And this is yet to be discovered across the facility that I can see. Right, going towards the end, because you're watching the news, yes. I'm gonna just brush through some example of these input setup and workflow management. So for instance, we have this ShapeSpire project that by now is quite mature, basically starting from an individual molecules allow you to set up the user different macromolecular aggregates out of that. It runs the simulation of MD or Monte Carlo. And as a result of that, you can also try to interpret, to simulate experimental fingerprintings, like for instance, small angle scattering. We have it here. And This can be quite powerful if given to an experienced user, because basically assist him throughout the full process from how do I start my simulation to how do I compare them with the experiment. Along the line of trajectories of molecular dynamics simulation, we have done something that is prompted by CLF experiments, where we basically have developed new theories of calculating orientational correlation function in the event of a chemical reaction environment, on a chemical event, because you're thinking of something that rotates, and then something that rotates undergoes chemical reaction, creates some question how to define the rotation. And we have a link with the code there that is being provided. We also have another possibility linked to the DL software, which is the DL analyze. So shortly, when you deal with condensed matter, the system is not symmetric. And instantaneously, you have a different local environments that are very difficult to characterize and to try to understand. And in this software, there is a new language that has been created to automatize the description of this local reaction environment, which might be useful, especially at the moment you want to go from structure resolution to reactivity. And is there, and you have the link. Right. Last but not least, as I was saying before, we also starting to have a growing offer in terms of machine learning interatomic potentials. And for example, this again in collaboration with ISIS, we have basically created this automated machine learning potential development workflow, where basically there is software that is a black box software that generates and optimizes machine learning potential until reaching a certain level of threshold, so that they can be used directly for simulation of certain properties, and the user just need to press the button. It's all hidden from him. But this is one of the kind of application that the facility might like. Of course, it doesn't come in 20 minutes. This has been 2 or 3 years of work. And this has already been used to study and interpret ISIS experiments on thermoelectric materials, because as I highlighted the special vibrational dynamics that was the experimentalists were not thinking of. Again, only by pressing a button, because it's all a black box. Now, has the machine learning potential become more accurate, also in terms of not only structure and dynamics, but also chemical reactivity? We've also started to work on this new generation of machine learning potential that allow to follow chemical events like molecular absorption or protonation or deprotonation of molecules inside the host. This is also, and in developing this, that has also been supported by the PSDI, there is already an existing infrastructure whereby the machine learning potential can become a library, or different machine learning parameterization can become different libraries. And the software infrastructure is already there. So this is for free, effectively, for the ASC, thanks to the PSDI. This is something we may want to explore together. So, to try to wake you up from the coma I've sent you, it was expected. I'm going to summarize the opportunities I see for us. As means SCD, as means STFC. We certainly have existing tools and experience that could be used in support of your experimental users. We are there, R89 at Desbury, and if you feel like putting your users in connection with us, we would be delighted. We can also develop, expand, or simply just teach how to use the existing workflows and user interface that we have. So work about in generation of input file and optimization of, especially for non-first principle levels of theory, is critical, and this we could also support and automatize things. And we could also provide a physical model to compare to data. So the beam scientist doesn't need necessarily to interpret the data in isolation with the user. Some of our software has been shown to be useful in planning the experiment, because you can get some features before measuring them, and when you get a deluge of data out of the experiment, this can be useful. And we are ambitious and arrogant enough that to think that we could play a role in developing new theory and approaches to really keep up with your facility development. And so theory-wise, these are the questions that we think we should be asking. So whatever you're going to ask in terms of theory and modeling, we are going to decompose that into our version. And in a more, let's say, accessible way, we can develop tools to bridge length and time scales. We would be very interested in a better treatment of solid materials versus isolated atom approaches for any kind of spectroscopy you measure. And this use of theory, not only to replicate the experimental observable, but also connect them, is something that we believe might generate value for STFC. To quickly give you some example, so this is something that, so in SCD, due to COSEC funding, we work on codes that are suitable for a core level spectroscopy, and especially we are interested in this crystal field. So typically, when you go from structure to the crystal field, fingerprinting in different kinds of core level spectroscopy or inelastic neutron scattering, you go through your quantity-based workflows that has atomic properties and allows you to interpret. So there is also the possibility of using an infrastructure that is half done, bar some theory development and just software work, to try to bring in a first principle derived parameters into the interpretation of this experiment. This is very complicated and it's not the job of one person. But if you want, we could also try to tackle this. And again, it's not going to be an SCD outcome. This is something that requires a different 3-4 people, if not more, just for the software development. And if you're curious, we have also categorized these workflows based on the software class that you have seen on slide 3. Another one, quickly, this just takes 10 seconds. So across the facility, there are different beamlines that measure structures, different beamlines that measure vibration, different beamlines that measure properties. I'm not going to comment on the level of connection between the facilities. I'm just going to observe that, oops, if we would like to try to link the structure to properties across facility, perhaps the development of a common software infrastructure could offer a bridge. And we are neutral, because the vibration for us are always the same, regardless of whether they're probed by laser, neutron, or any other way. Last but not least, most of the stuff I've shown you is about ground state methods. However, if you look at all the great programs and agenda for facility development, high pressure lattices, maximally increased brightness at diamond, UKXFL, so we're going to do a time resolved core level spectroscopy, ILAX, Artemis and Ultra at CLF, EPAC no less. We are all going to bang our head against matter out of equilibrium or at the extreme. And their theory is, as always, 20 years behind. So in supporting the facilities, there is a lot of stuff that could be shared, not only between operando electrochemistry and photoelectrochemistry, but also the local and instantaneous static or dynamic nanostructuring for a plethora of physical properties and regimes that you're going to generate at the facility. We are not ready. Maybe your users are ready to interpret these experiments, but this could be also something you may want to tackle. To conclude, as we started, so the Ada Lovelace Centre is a scientific computing center with the primary objective of enhancing the scientific, probably I should have underlined that, impact of the STFC large-scale national facility. And this stress on going from isolated projects to a wider strategy, that of course needs to be agreed collectively, is going to be there. And this needs to be aligned to your vision and needs, and it should be long-term and sustained, and it should be in some way coordinated. And that's why we are going this workshop. So this was me regurgitating terabytes to you about what we have. You have the links. If you do some homework, then you can refine what you want. You're not obliged to suggest all it all, because we're not going to have enough FTs. So maybe the facilities can pick up what they think is more important, and then we can move from there. Because there is really a lot. And some of it might not be, you might not have been aware. Because SCD, what does it do? Digital infrastructure. But we also do the stuff I presented. So, This is the last slide, and then if you have questions, I can try to reply to them, so we'll help Paul. In a way or another, in STFC, we measure and characterize structural and electronic properties. In doing so, some of the facilities need to develop some kind of engineering or facility development or facility materials development is involved. So we know how to write code for doing computational material science. We know how to use that. We have also been using it to do research. So if there is something that you may wish to use our expertise for, we would be very happy. When you request, it would be very useful, or when you state your priority, and we really want this, slamming fists or shoes a la Crucial, it would be useful if you use the software categorization. You can find a software on slides 2 and 3. So this is going to streamline the discussion. Then we would be very much interested in knowing what are your priorities for modeling and simulation, what are the developments? You want better workflows, you want better theory, you want, I don't know. So what are the developments? Not just bringing what is existing at the moment, but also what do you need new? What needs to be created? Because we don't know it. You might have some problems we are unaware of. And then this is more for you. So based on your experience and given for granted that the facilities know what the users want, what would be the best way of interacting for the theory, modeling, simulation with your users? Just backend, give the software, and we don't exist. Do you want to have scientific collaboration? So this I think it would help still in the discussion. Then most likely, or is it possible that we are going to repeat this talk in a week? I don't know it yet, but if you have questions, feel free to contact me and Paul, and we can, I'm always here at trial, we can continue the discussion, because I'm sure that this doesn't cover it all or doesn't explain it all. There is just too much stuff. So if you want to follow up in discussions, I cannot decide anything because he's the director, but I'm very happy to give clarification. Okay, thank you.